In Chapter 4, we're going to talk about systems of linear equations with two variables. So the form for a linear equation, the standard form, is ax plus by equals c. And we worked on those in Chapter 3 where we were graphing linear equations. Sometimes we put it in slope-intercept form to graph it or other things. But now in a system of equations, we're going to have two lines, okay? Or two equations, I should say. You can have more than two, but some of ours will just have two. So maybe I have something like 3x plus 4y equals 12. And I know I could graph that line. I could make a table of values. I could use the intercept method, or I can put it in slope-intercept form and graph it using the slope and the y-intercept. And then maybe I have another equation that says x minus y equals 3. And I know I could graph that equation, right? Okay, but the solutions, let me back up a minute. So for this line, it graphs, and there's a lot of ordered pairs that make that equation true. Actually, it would go the other way because the slope would be negative, but it graphs to be a line. And then this equation also graphs to be a line, like that. And it has a lot of points that make the equation true. And you can think of the ordered pairs that make that equation true. There's an infinite number. When we're talking about solutions to a system, we're looking for points that make both equations true, or that satisfy, I'll say satisfy, both equations. Now there might be one point that satisfies both equations, there might be an infinite number of points, or there might not be any. So in example 1 here, they give us a system of equations. Now here's the system of equations right here. This brace right here is just so that you know that they're talking about those two equations together. That's the system. So in order for it to be a system of equations, you have to have two or more equations. And this one has two equations, okay? And it says determine whether the ordered pair is a solution to the system. So what you do is you take this on part A here. We're going to take 1, -3, and I'll just put it in the top equation first. So I'm going to say 3 times, well, let me write this out so it's a little bit clearer. So I'm going to take the equation 3x plus y equals 0. What I'm going to do is I'm going to plug in this ordered pair and see if it works. So I'm going to have 3 times 1 plus a -3. Does that equal 0? Well, 3 plus -3, that equals 0. So yes, it works for the first one. I'll put a little check, because it doesn't mean it works for the whole system. It has to work in both equations. So now I'm going to try the other equation. The other equation says x plus 2y equals -5. So I'm going to plug in the 1 for x, 2 times -3, and does that equal -5? Well, 1 plus -6 equals -5. Yeah, that's true too, isn't it? Okay, so it makes both equations true. So yes, this is a solution. Yes, a solution. A solution to the system. It has to make both equations true. Okay, for part B, we're going to do the same thing. We just have a different ordered pair. So we take the 3x plus y equals 0, plug in 0 for x and 0 for y, and we get 0 equals 0, so that part's true. Now I'm going to take the other equation, x plus 2y equals -5, and plug in 0 for x, 0 for y, and I get 0 plus 0 equals -5. That is not true. Not true. So no, this point is not a solution. No, not a solution. So if an ordered pair is going to be a solution to a system of equations, it has to work for all the equations.